Okay, in this podcast we're going to talk about what are the trends for atomic and ionic radius sizes. If you want to follow along in the text, it is section 7.3. Okay, so let's first talk about what we mean by the size of the atom. When we're talking about the size, we're really talking about the volume. We can also talk about the radius, and in fact, most of these trends we're talking about radius. So it's really hard to measure the radius of an atom because not only can't you see it very easily, but this area on the outside is really very diffuse, right? So it's not like it's got a sharp line. So what scientists use instead was they say if we have two atoms that collide, that the radius or the distance between the two nuclei would be the distance, and that the radius of each individual atom would be 1/2 of that distance. Okay, so that would be the radius of a given atom. That's how they, conceptually think about radius. All right, so let's just take a look. Here are the trends with size. So think about what you can see in those trends. What would you say? All right, so let's talk about this. So we see a trend where as we go down a group, we increase in size. And we see a general trend as we go across, we decrease in size. So let's talk about why that is. So in order to talk about size, let's think of a specific example. So let's imagine we're starting with a neon atom. And the neon atom is going to be right here, right? And let's take a look at building an atom or a series of atoms in the third period using neon as the core. Okay, so if I do that, neon has 10 electrons in its nucleus. 10 protons in its nucleus, and it's got 10 electrons. If I get to sodium, I am adding an additional energy level. And therefore, this is going up. Now, it's not showing it going up as much as I would have liked, but we should show this. Sodium, the size is going up. Okay? And that is because I am adding an additional shell or additional energy level, which is that electron is further away from the nucleus. Okay, so what happens from there? So now I still have the same core, right? And the core, if I think about it, that provides the shielding, is shielding with 10 electrons, right? So here I am adding an electron, and it is feeling an effective nuclear charge of +1, right? What happens when I get here is now I am increasing my nuclear charge, and I am not increasing my shielding. My shielding stays the same, and I'm increasing the number of electrons out here. So as I do that, now I have an effective nuclear charge of 2 plus 2 electrons. If you think about Coulomb's law, Q1, Q2 over R. R is essentially the same distance for magnesium as it is for sodium, but I have doubled Q1 and Q2, so I'm significantly increasing the attraction these electrons have for the nucleus, causing them to be pulled in. Same thing happens, of course, as I go across to aluminum and silicon and phosphorus. When I get to phosphorus, now I have 15 protons in the core or in the nucleus. I have the same size core as I had up here with sodium, but now I have 5 more electrons, 5 more protons, and my Coulombic attractions just get that much larger. So I am the same distance from the core, but my effective nuclear charge is increasing, and my number of electrons out here is increasing. All of that causes these electrons to be pulled in closer to that nucleus. Okay, so give it some thought. As we proceed across the row of the periodic table, the atomic weight increases, but the atomic radius decreases. Is this a contradiction? So think about that for a second. Okay, so if we think about what's happening, let's go back and take a look at the picture. Okay, go ahead and try to answer this question. Order the following according to the increasing atomic radius. And then come back. All right, so let's orient ourselves with what we have here. We have gallium, silicon, selenium, and chlorine. So we have sort of this area here. So the first thing we have is we are going down a group, which means we are adding an additional shell, kind of like another layer of the onion, and we're going across, and as we go across, we're going to increase our effective nuclear charge. So the question is, which of those has the bigger effect? And the answer to that is adding an additional shell is going to cause things to change faster than moving across the period, okay? Because we're adding something at a further distance. So the larger two are going to be germanium and selenium. So if we are looking at this row then, trying to figure out which of those two is going to be the larger, germanium is going to have a lower effective nuclear charge and the same shielding as selenium. So germanium is going to be the largest. And there's only one here that has germanium being the largest. Okay, so it's important that you're able to say why that is. These are the questions that get asked all the time on FRQs for AP Chem. Why is germanium larger than arsenic? So you have to think about the fact that they have the same distance, their outer electron has the same distance to the nucleus, that it has the same number of energy levels, but arsenic has one more electron and one more proton, causing, you could say, greater Coulombic attractions, or you can say greater ZEF, greater effective nuclear charge. So be careful, a trend is not an explanation. Okay, how about this question? Based on atomic radii, which of the following bonds would you expect to be the shortest? Okay. So the bond is going to be the distance between the nuclei, right? So we're going to have to look for the atom the atoms involved that are the smallest, and those that are the smallest are going to be hydrogen, and therefore the hydrogen molecule. All right, so let's talk about sizes of ions. Now here's just a picture that shows both the sizes of the ions and the sizes of the atoms. It's a little bit busy. But what's important is that when we are thinking about what's happening with ions, we need to think about several things. We need to think about the nuclear charge, how many electrons we have, and where those electrons are located. All right, we're going to start off with cations, which tend to be metals that will lose electrons and become positively charged. Okay, so a lithium cation is significantly smaller than the lithium atom. So think about why that might be, and then we'll talk about it. Okay, so if we think about, this is the lithium ion, the lithium atom. It's got three protons in the nucleus. It's got 3 electrons, 1 electron in the valence shell. When it loses an electron, it loses this electron, and it loses that whole outer shell. So the reason it becomes smaller is that the outermost energy level is removed. And that's almost always what's happening when a cation is formed. It is losing its valence electrons, losing the that energy level on the outside, causing it to be smaller. All right, anions, nonmetals, which tend to gain electrons, become anions. And the anions are almost always larger than their parent atom. So let's think about what's happening here. So if you look at what's happening with chlorine, here's the chlorine atom, right? And here is the chlorine ion. So I have the same number of protons and neutrons in the nucleus. I have the same core, same amount of shielding, right? The only difference is I've added an electron out here when I make it an ion. So what does that electron do? That electron creates more repulsion. There is repulsion amongst these electrons here, and that additional electron causes more repulsion. It's not going to be any more attracted to the nucleus because the effective nuclear charge doesn't change, right? So the electrons are added, causing more repulsions, and that is the explanation for that one. Okay, so ions increase in size as you go down a column, and that is simply due to the addition of the additional energy level further away from the nucleus. All right, so let's talk about the size trend in an isoelectronic series. So if you remember, an isoelectronic series is one where the electron configuration is the same for different elements. So this is an isoelectronic series. All of these atoms have the electron configuration of neon, right? Here we have the sodium loses an electron and becomes like neon. The magnesium loses 2 electrons, becomes like neon. The oxygen here gains 2 electrons to become like neon. So all of these have the same electron configuration. Now their neutral atoms are different, but their electron configurations are the same. So their electrons are the same. What's the only thing that's changing? The only thing that's changing is the number of protons in the nucleus. So in an isoelectronic series, as you increase the nuclear charge, you are making the atom smaller because these electrons now are more attracted to that higher effective nuclear charge. Okay, so isoelectronic series, ions have the same number of electrons and the same number of energy levels, in that in general, ionic size will decrease with increasing nuclear charge. Okay, number of protons. All right, so which is larger? Think about this for a second. Is it going to be sodium or sodium plus? All right. Sodium has an additional energy level, right? When it becomes sodium plus, it loses an outside energy level. So the sodium is larger than its ion. How about chlorine? What's going to happen with chlorine? All right, the chlorine atom in the chlorine ion has the same number of protons, but the additional chlorine ion or electron is going to cause more repulsion and therefore cause that atom to be larger, more spread out, less attracted to the nucleus. All right, we're going to stop right there.